Okay, today we want to talk about drainage system design and layout. Now, this is a flow chart of the drainage design process, and this was prepared by Gary Sands from the University of Minnesota. First of all, we collect background information on soil, the topography, and crops. We determine if drainage is needed. If drainage is needed, the first thing to do is to find an outlet, a suitable outlet for the drainage system. After we have done that, we select the design intensity and also the resulting depth and spacing. We develop a layout of the system. We determine grades and depths. We determine the drain size, and then the final step will be the installation. Today we want to talk a little bit about selecting a drainage intensity and depth and spacing and laying out the system. So the drainage intensity, it represents the drainage rate in which when the water table is midway between the drains and coincident with the soil surface. And this is the rate at which water would enter into the drains. Sorry, the drainage intensity is usually estimated using the Hoogout equation, and it is dependent on the saturated hydraulic conductivity of the profile, entry resistance into the drain pipe, drain depth, spacing, and depth of the soil profile or a restrictive layer in the system. The drainage intensity usually is anywhere from 3/8 to half an inch for mineral soils. If we're dealing with field crops, such as like tomatoes or other vegetables, then a higher drainage intensity is used. Usually then it's between 0.5 and 1 inch for mineral soils and up to an inch or inch and a half for organic soil. Incidentally, the highest drainage intensity is usually used for golf course, which is indeed a high value crop, with drainage intensities of up to 6 inches per day. The drainage intensity is a function of the depth and spacing. In other words, for different combination of depth and spacing, one gets the same drainage intensity. These are three curves for one soil. This happens to be Drummer, where you can see that a drainage coefficient of 3/8 inch could be achieved with having laterals 60 feet apart, 2.5 feet deep, or 100 feet apart, 5 feet deep. And then the determination of the depth and spacing would be based not on the intensity, but on other considerations. Here is an example of a calculation of the drainage intensity for a system. And here we have a tile at a depth of 4 feet, 6 feet to the impermeable layer. And this is for Drummer soil. And the drainage intensity from this calculation is 3/8 inch or 0.375 inches. This is the rate at which water would enter the tiles under the assumption of an elliptic water table with the midpoint just touching the surface. However, this is not the maximum rate at which water can enter the soil. A better measure of the maximum rate at which water can enter the soil with the water table at the surface is given by the Kirkham equation. And the Kirkham equation, usually the tile, there is pressure on the tiles and more water enters the system than is given by the drainage intensity. In this particular instance, on one of the same parameters, the Kirkham coefficient would be roughly 1.5 inches per day, which is about 4 times the drainage intensity. And That the other component then would be the drainage coefficient, at which is the rate at which water would drain from the system through the pipes. And this is dependent on the nature of the pipe material as well as the slope. And this is given by the Manning equation. Now, typically, the drainage systems are designed so that the drainage coefficient is equal to or in excess of the drainage intensity. If the drainage coefficient, which is the capacity of the pipes, is more than the drainage intensity, then in periods of heavy rain or saturation, when the flow through into the pipes exceeds the drainage intensity, the system would still be able to handle it. Now, when possible, once one has determined the depth and spacing, when possible, subsurface drains should be placed at a uniform depth or as uniform as possible. The range of slopes or grades at which they can be placed depends to some degree upon the topography of the land. The grade should be great enough to prevent silting, but flat enough to prevent the flow from exceeding the allowable velocity and subjecting the drain to excessive pressures. This is really high with current plastic system, so it's not much of a consideration. The upper grade on tiles is not much of a consideration these days. The grade should be as steep as possible on flatlands so that the size of the pipes can be minimized. However, adequate drain depth should not be sacrificed for increased grade. Here are general recommendations for depth and spacing for different soil types. However, with the advent of online database and drainage design tools, there is but little need for using these general values. For example, this is a tool out of Michigan State that determines the most economical drain spacing for a given depth for specified locations in the Midwest. And this is optimized so that one would get the optimum economic return on the drainage investment. The Illinois Drainage Guide has a tool for simulating drainage for different soils, mainly soils in Illinois and Wisconsin, and looks at the effect of depth and spacing on yield or on several other properties, such as the drain volume, etc. And one thing about this tool that it contains data not only for current condition, but also for projected weather conditions in the mid-century and also at the end of the century. After one selects the drainage intensity and the depth and spacing, the next step is to determine the system layout. This is the most important step in the drainage system, in the drainage design, besides determining the outlet. The outlet, having an adequate outlet becomes more and more of a problem as more systems are installed. The easiest jobs are already done. And then with more systems, it becomes more difficult to determine suitable outlets, or the main has to be decoupled from the laterals. You could have a long main, which travels some distance from the field, which would affect the cost. Well, the layout determines the uniformity of drainage, and the objective is to have as uniform depth as possible so that the crop growth will be as uniform as possible. It is recommended that one should always start with a topographical map of the field, the entire field. And with the advent of LiDAR, one can determine the location of the field within a watershed or a sub-watershed, and therefore can determine what future drainage needs may be for this particular system. And that comes in sizing the mains. The layout of the system can be, there are several different patterns that may be used. The common systems are the parallel systems, the herringbone systems, in which laterals enter from both sides, and also the targeted systems or irregular systems, haphazard systems, where tiles are put in a wet spot in the field, and the entire field isn't covered. Previous to the advent of the yield monitor, most systems installed in the Midwest were these targeted systems. However, with the advent of the yield monitor, and where it was shown that yields varied with distance from the tile drains, with the highest yield being over the drains, then more pattern systems are being installed. In laying out the system, there are essentially two options for optimizing the layout. The system can be optimized for the cost of installation. To optimize the system for the cost of installation, the laterals would be perpendicular to the contour lines, so they are steepest, and hence for a given flow they would be the smallest. And if they're optimized for drainage water management or for sub irrigation, then the laterals would be run more or less parallel to the contour systems. And this way, it is possible to define zones in a particular field that can be used either for sub-irrigation or drainage water management. For drainage water management, zones should be 2 feet or less. They should cover a range 2 feet of elevation change. Whereas for sub-irrigation, according to the NRCS practice standard, the zone should cover a 1 foot change in elevation or less. After the system has been laid out, the next step is to determine the drain depth and grade and size for each pipe. In general, slopes should not be less than 0.1%, and the depth range should be kept as narrow as possible. With the new drainage material, there is no limitations on the maximum slope, although the maximum slope that is generally used is a 5%, but there is no limitations on the maximum grade that with the new plastic pipes. Minimum grade is usually set at 0.1% or 1 foot in 1,000 feet. And the reason why this is typically set as a minimum, it's because it is the maximum, it is a minimum grade at which a tile machine can install tile at a reasonable speed to make the process profitable. For flatter grades, the installation will have to be slower. And say if, for example, one use 1/2 of a tenth, then the speed of the machine has to be less than 1 mile per hour. And so unless there is a definite reason for doing so, tile minimum installation slopes are usually 0.1%. Care should be taken not to have the drains too shallow. They should be placed below the mean annual depth of frost penetration to prevent frost heaving. There are several commercial packages for determining depth, and for laying out drainage system, determining pipe size and grades. And for example, there is AGPS and Tremble are two main commercial systems. Here at Illinois, we have developed a set of tools that they're exploded so that we can see the various steps in the layout and in the design layout and design procedure for depth and spacing. And these are GIS plugins that can be used. And in the next section, we will go through an example of using the Allina drainage tools to lay out a system. Thank you very much.